Chapter 15, Agua. Let's do a little review about water molecules. O is more electronegative than H. O, oxygen, wants that electron more than H. So that means O has a partial negative charge. It's pulling on that electron much more than hydrogen is. So it's partial negative. And it causes the molecule to be a bent shape. And it becomes polar because of it. And because of the polarity, you have these hydrogen bonds between that, the water and other water molecules or other things. Strong hydrogen bonds there. So water molecules are attracted to one another better than other molecules at size. The strong hydrogen bonds will make it very hard for water to become a gas, because these hydrogen bonds here are just holding on to each other. Those water molecules are really holding on to each other pretty strong. Now, because of hydrogen bonding, water has very strong surface tension, which means that liquid water acts like a skin. And here we have a scary spider just being able to chill on some water because of the strong surface tension. Water will form round drops, and this is all because of hydrogen bonds. If you ever look at a drop of water, let's say if someone's crying there, of happiness, he's crying because he's happy, we have round spheres, and this is all because of hydrogen bonds. Now, not all liquid will drop in spheres, because they all don't have these hydrogen bonds. Now let's look at surface tension. Here are the hydrogen bonds between the water molecules that causes surface tension. And one water molecule H bonds to another, and can hydrogen bond to molecules all around it, as we talked about in a previous chapter. Here we have the water molecule having these hydrogen bonds with other water molecules, and it creates surface tension. Now the water molecule in the middle of a solution is pulled in all directions because of the hydrogen bonds here. These are the H bonds. So that's what gives water its really neat properties, all these hydrogen bonds. Like a little network here, it's almost like a little net that creates a surface tension. That hydrogen bonds will pull, these are the hydrogen bonds here, the white is the hydrogen bonds, they pull the water molecules together, the yellow are the water molecules, and they create a system there that creates the surface tension, and which gives it its circular shape here. It's just pulling in, it's just more stable. So here we have all the hydrogen bonds forming, causing a sphere to form. And here's a real live picture of a sphere of water. So water drops are pulled around because of all the molecules on the edge are pulled toward the middle. Gravity will flatten them out on the surface. That's why you don't, when you put a drop of water, it's not a perfect sphere like that anymore. Just gravity will flatten it. Remember our friend vapor pressure. Vapor pressure is the pressure caused by the vapor above a liquid at equilibrium. So if we have a liquid here, remember things will evaporate. Water molecules, for example, will evaporate and go into vapor and create a pressure caused by the molecules that escape. Water has a low vapor pressure for such a small molecule. Now the hydrogen bonding will keep molecules from escaping. They just hold on to each other. So if a water molecule wants to say, I want to go, I want to go, I want to go, well, it's hydrogen bonded to another water molecule that says, no, stay here, I'm bonded to you. So it's a hydrogen bond that keeps it from escaping. When vapor pressure equals external pressure, we have boiling point. We have boiling. Those strong hydrogen bonds that keep those vapor in, don't leave, make it hard for water to become a gas. Thus, we have a pretty high boiling point, 100 degrees Celsius. Now let's just quickly look at the structure of ice. Most liquids will contract and get smaller as they are cooled because the kinetic energy is slowing down, and they're just being able to, they don't have that vibration as they do in the liquid phase or the gas phase, so they get smaller, more dense. They get much more dense than their liquid phase. When they change to solid, they're more dense than the liquid, as just mentioned. The solid metals, for example, will sink in liquid metal. So if we heat up a metal to extremely high temperatures, it will become less dense. As we cool it, they tighten, they contract, they get more dense. And if we put those liquid or the solid metals in liquid, they will sink because they're more dense. However, ice, solid water, will float in water. As you know, if you have a drink, those ice cubes will float. It would be kind of strange if you had a drink and then you put ice cubes in it and they all sank to the bottom. That would be weird. I wouldn't drink that. Now, why does ice float when most all other liquids or most all other compounds change and become more dense when they become solids? Water, interestingly enough, will become more dense as it cools until it reaches 4 degrees Celsius. Then something happens. It becomes less dense. They start to spread out. The molecules slow down. They arrange themselves into a honeycomb-shaped crystal. Now, I know when you hear the word honeycomb, you think of honeycomb cereal, tasty stuff. Now, this is a box when I was a kid. They had this really cool commercial about the honeycomb hideout, and that boy on the cover was, I think, the leader. And I always wanted to be in the honeycomb gang and have a hideout. So I tried to get a hideout by getting a big cardboard box, but it was just kind of was a big fail. But anyway, honeycomb-shaped crystals. This is what it might look like, water. The ones with the red dots in it would be oxygen. It should have a red dot in there. And the ones without a dot would be hydrogen. And we'd have those hydrogen bonds would be the yellow or the red. So they would arrange themselves into a more stable configuration. It's much more stable at such a low energy, at lower kinetic energy, to be in this honeycomb crystal shape. And this makes it less dense. And they're, as mentioned, held together by H bonds, hydrogen bonds. Freezes at 0, which is high for a small molecule. It's 10% less dense than liquid water, we should say. Water will freeze from the top down, as you know, and that's really important when it comes to lakes and ponds, because the poor little fishies, what would happen if it froze the other way around? The little sea life would be no longer existing. So it was nice that water does that. And also what it does, it creates kind of an insulation. So while you guys are ice skating up here, or doing whatever, the little fish are happily swimming along with a nice ice roof. There's a liquid diagram. Although hydrogen bonds aren't between everything, just some of them. And here's a nice solid hydrogen bonding crystal structure, honeycomb crystal structure. And notice that we just have bonds. The energy slows down so much that those hydrogen bonds can form. It's like if people are out there dancing and they're just moving too fast with a cool groove, too much, but we slow it down, they can slow down and they can start holding hands. Now here's a snowflakes, all because of the hydrogen bonding. They do it in, now, as we know, snowflakes, there are many patterns of snowflakes, uncountable patterns of snowflakes, and all due to the hydrogen bonding and much more stable structure like this. To look at aqueous solutions, now a solution like Coca-Cola is just a homogeneous mixture, mixed molecule by molecule. So homogeneous, homo means it's the same throughout, as opposed to a heterogeneous mixture. So a solution like Coca-Cola, or any sort of cola, like 7-Up or Sprite, is a solution. And a solution is made up of a solvent, the stuff that does the dissolving, such as the agua. So the solvent does a dissolving. High fructose corn syrup is often the solvent or sugar in cola. Usually now it's high fructose corn syrup because it's much cheaper than sugar. I was in a restaurant, I can't remember where, I think it was probably in Michigan, but they are advertising a special deal of having, they had Mexican Coke, because the Coke from Mexico has sugar in it as opposed to the high fructose corn syrup that is in an American Coke. We can have solvent, solute, and solutions existing in all phases. Aqueous solution, a solution with water is the solvent. Here is an example of a solute. Our favorite solute, probably everyone's favorite solute, is Kool-Aid. Here's a solute, our favorite Kool-Aid. A solvent is the water, and here's our solution. Nice ice cold glass of Kool-Aid, cherry Kool-Aid. Now Kool-Aid is also very tasty if you take that ice out and heat it up and have a nice warm glass of Kool-Aid on a summer day. So aqueous solutions are those with water as solvents. Now, the interesting thing here is that water will dissolve ionic solids and polar covalent solids the best. There's the rule of like will dissolve like. Now water is polar. Here we have a polar, has two poles to it, positive and negative. So since it has charges, it will dissolve other things that have a charge or partial charge. Polar dissolves polar, non-polar dissolves non-polar. Oil is non-polar. That's why you can put as much oil as you can stir and shake it up, but it will not dissolve in water. It's non-polar. It hates polar. Non-polar things are hydrophobic. They despise water. Oil and water, of course, don't mix. Salt is ionic. That means it has charges. Any polar will dissolve ionic. For example, here we have the sodium is small, the chlorine is large. Here's the sodium, here's the chlorine. Around here, it's water. All these little black and blue little Mickey Mouse things are water. Sodium chloride is immersed, and then we have all the water molecules attracted to it. The chlorine is attracted to the positive end of the water, and the sodium plus attracts to the negative end of the water, the oxygen, and here's the hydrogen. And they come and take it. And now I'm going to show you a pretty cool animation pretty soon. That's called solvation. Water breaks the plus and minus charge pieces apart and surround them and rips them across. Okay, so let's check this out. Here comes a water molecule. Hey! What does this remind you of? It reminds you probably of some Sacred Heart girls and a VFC or HBB, Heartbeat Boys. Varsity Fan Club or Heartbeat Boys, they're here, they're chilling. Here comes some Sacred Heart girls. Oh my gosh, look, it's Noel. And they come take him away because of that attraction. Hydrogen has a plus charge, partial plus charge. Here, oxygen has a negative charge. And a whole group surrounds David. Another group will surround another one of the HBB or VFC. It could be Brock. Let's take a look at another cool animation. Okay, watch this. All those water molecules come and take that chlorine away. I'll play that again. So those hydrogens are attracted to the chlorine. And notice those positive attack the negative. When an ionic compound dissolves in water, water molecules separate, surrounds, and disperse the ions into the liquid. Note that the positive ends of the water molecules face the negative ions. And let's look at this close-up view. Here they come. It's like, oh my gosh, it's Jake from the Varsity Fan Club. Ooh! Play that again. Oh my gosh, it's Drew from the Varsity Fan Club. Oh my gosh. Oh my gosh, and now here's Cody. We're so attracted to him. Oh, so they go take him. Here we go, look at this. The oxygen is now getting the sodium. And they take it away. They were attracted to it. Note that the negative ends of the water molecules face the positive ions. So this is just like some Ash girls coming. Oh, there's Cody from the Heartbeat Boys. Oh my gosh. And they just surround him and take him away. It's that chemistry. It's the attraction that causes dissolving.